Okay, this video is on electronegativity and bond polarity. So first thing we're going to do is we're going to define what electronegativity is, and that definition being the tendency of an atom in a molecule to attract shared electrons to itself. So these shared electrons obviously are going to be within a bond, okay, within a covalent bond. So they're being shared between, say, element X or element A and element X. Okay, they are sharing these two electrons right here, but they may not be sharing them evenly because if, let's say, X has a high electronegativity, that means the electrons that are being shared, okay, these two electrons, they may want to be, more towards the X atom versus the A atom. Okay, and what can actually happen is if that is a strong enough tendency or a strong enough attraction, then we can actually better define the type of covalent bond it is. Because in truth, there are not just covalent bonds and ionic bonds. There's actually two different types of covalent bonds. And those bonds are called polar covalent and non-polar covalent. So those polar covalent bonds, that's when you're going to have an uneven sharing. Good way of putting it. So an uneven sharing of the electrons, and then a nonpolar covalent is even sharing. They're sharing them equally. Okay. The way I usually like to put electronegativity is atoms that have high electronegativities are very greedy, and they don't like to share very well. They'll still be willing to share just to appease mom and dad, but they don't like to share very well. So the polar covalent, those would be uneven sharing, and then non-polar covalent, which would be an even sharing. Now, how we determine whether or not something is a polar covalent bond, a non-polar covalent bond, or even an ionic bond has to do with their electronegativity values, which you may see me write like that, and that would be electronegativity. But if you look on page 403 of your textbook, there's actually a periodic table that has the electronegativity values on the actual tiles of the periodic table. And it also gives you the trend of electronegativity. Electronegativity is just like ionization energy. It's just like atomic radius. There are trends to it, okay? And we can see the electronegativity values increase or decrease as you go across a period or as you go down a group. Now, it just so happens that the electronegativity trend is the same as ionization energy trend, which was if you go left to right across a period, electronegativity is going to increase, and if you go up a group, electronegativity is going to increase. So this is going to show an increase in electronegativity. Okay. Now, a couple things we should know. Noble gases, okay, they do not have electronegativity values because the whole point of an electronegativity value is to see the tendency of atoms to want electrons when they're bonded. And since noble gases really don't bond, they don't really have electronegativity values. So we would not need to worry about, say helium being the most electronegative, when in fact fluorine is the most electronegative atom or element. So when it comes to deciding the values for electronegativity, the number itself, okay, the scale goes from 0 to 4. Okay, and they're usually written in the 10th place. So it'd be like 0.0, or the lowest value, which is francium, is 0.7, and then the highest value is 4.0. So francium, okay, francium has a 0.7 electronegativity. There is no unit for this, okay, just 0.7 electronegativity, and then fluorine would be the highest at 4.0. Okay. Now, if I wanted to like I said, determine polar covalent or non-polar covalent, what I need to do is I need to look at the difference. Okay, I need to do some subtraction to find out what's the difference in electronegativity. Right? So if the difference in electronegativity is greater than 2, okay, so if I was to take two atoms that are in a bond and I subtract their electronegativity values, obviously getting the absolute value, um, and that change, okay, that's what delta is. This little delta right here means change. Okay, if the change is greater than 2, then that's going to be indicative of an ionic bond. Okay, if the change is less than 2 but greater than 0.4, so the difference between the electronegativity values of the atoms are less than 2 but greater than 0.4, then we have a polar covalent bond. And lastly, if we have the change being less than zero point 0.4, then we would just call it a covalent or a non-polar covalent bond. Okay, just so we see what these guys look like. Okay, a non-polar covalent bond, as you can see, the evenness within the red showing that the electron clouds are not being distributed towards A or B. They're evenly distributed, which means A and B are sharing nicely. Okay, but if we look at the polar covalent, we notice that B has more electrons around it because it has a higher electronegativity value, and it just so happens that the difference between A and B must be between 0.4 and 2. That makes it a polar covalent bond. And then, of course, if it is greater than 2, you'll notice that there is no bond for the ionic bond. So here's your, red doesn't necessarily work right there. So there's your 2 electrons that are being shared there. Here's your 2 electrons being shared on the polar covalent bond right there. But if you look on the ionic bond, there is no sharing going on. They just flat out, A gave away its electron to B, which forms the ions, and of course the ions are what attract each other and have that ionic bond forming. So let's go ahead and do a few examples and then determine if a bond is in fact polar or not. All right, so in these 4 examples, we're looking at the red covalent bonds. In the first one, we're looking at, let's see, we'll go ahead and say 1, 2, 3, and 4. And the first bond is a carbon-oxygen bond. And what we're going to do is we're going to take the difference in electronegativity between carbon and oxygen, that being 3.5 for oxygen, and then 2.5 for carbon. That's a difference of 1.0, which means this would be a polar covalent bond. Now, how I show that there is a polar bond there, polar meaning that electrons are on one side more than the other, the way I show a polar covalent bond, or what we call a dipole, okay, or even a dipole moment, is when I draw an arrow like so. Okay, kind of see this as a little plus right here, saying that if all the electrons are over on the oxygen side, that means the carbon must have a slight positive charge to it. That's where we got like the slightly negative and slightly positive when we started talking about the polarity of water. Okay, in this case, carbon would be slightly positive and oxygen would be slightly negative. Okay, I'll go and look at number 2. Number 2 is 2.5 for sulfur and 2.5 for carbon. So as it turns out, this is a non-polar covalent bond, so I do not draw my little dipole moment arrow with the plus thing. I don't draw that. Okay? The phosphorus, carbon-phosphorus bond, phosphorus is 2.1 and carbon is 2.5. The difference, remember we're getting a absolute value, would be 0.4. And according to this, this is a slightly polar bond. But what we're going to do here is I'm going to change my graphic a little bit. Okay, I'm going to go back to this. And we're going to go ahead and say if it's greater than or equal to, oops, not that one. If it's greater than or equal to 2, it's ionic, or if it's less than or equal to 0.4, then it's covalent. Okay, so in this case, the 0.4 for the carbon-phosphorus bond, it would be a non-polar covalent bond, which means I don't draw a dipole. And then carbon-hydrogen, carbon is, or hydrogen is 2.1 again, just like phosphorus, and then minus 2.5, that'd be 0.4, so this would be a non-polar covalent bond, okay? But just so you guys see, this right here is what we call a dipole moment, meaning or a dipole. The electrons are all heading towards one side because they do not share evenly between the oxygen and the carbon, okay? And you usually can show the polarity of a bond just by having these little dipoles drawn in your bonding. Okay, so we'll do a quick molecule so we can see. So here we have fluoromethane. When I say, okay, find, and this is what you'll have to do for your worksheet, I'll say, for each of the bonds in a structural formula, determine the bond polarity, and if it is polar, to draw a dipole. So, for example, with the carbon-hydrogen, there is no dipole, so I won't draw a dipole moment because if I know that 2.5 of carbon minus the 2.1 of hydrogen is going to equal 0.4, which means that's non-polar. But if I was to look at the 4.0 of fluorine and I subtract the 2.5 of carbon, then I'm going to end up with 1.5, which most definitely is a polar covalent bond between the carbon and the hydrogen. And remember, the arrow is always going to point to the higher electronegativity value, in this case fluorine, so I would do that, and that would be my answer. Okay, if you have any questions, please ask.